Hello, Zeron. Seems you have a question.
Yeah, hi Scott.
Presuming
I
this
have a
thing's got the
question
right thing, yeah.
about
Right.
the line pre-charge.
Maybe not then.
Hello.
Right, where do we get to? We are here in the lecture. Yeah. That's presuming I've got the audio set to the right thing, that is. Probably didn't. Uh, I might have had my audio set to the wrong thing, so do you want to try again? Yeah, I can hear you. Yes, yep. Right, was it for a read or a write? Right, okay. So what we do is if we're going to read some data, right, we've got some data stored in the cell, and in fact, where's the. Let's have a quick. Let's just bring up the particular slide. So we've got some data stored in this bistable inverter circuit, right? And we want to know what that data is, right? Um, so what we do is we say, right, we're going to have these two lines, one on either side, bit line and bit line not, right? And then what we say is we're going to pre-charge them. We're going to charge up all the parasitic capacitance, the intrinsic capacitance on that line. And then we're going to let our bistable circuit discharge whichever one shouldn't be high, right? So if we're storing a 1 in the circuit, we'll see that the bit line remains charged because the bistable circuit is outputting a 1 on that side, whereas the inverted bit line over here will end up being discharged by that bistable circuit because the inverted output of the bistable circuit is a 0, so it discharges the inverted bit line, right? Yes. So we are still looking at capacitances to a certain extent here. Yeah, it's not quite sequential dynamic because there is a regenerative section in the center here. But yes, what we're doing is we're charging up parasitic intrinsic capacitances on either side of the cell and then using whichever inverter is outputting a 0 to discharge the appropriate bit line or inverted bit line, right? Sapping all the charge out of the parasitic capacitance, right? No, they are different from a flip-flop or a latch. So a flip-flop is edge triggered, and a latch is is value triggered, right? So you've got a flip flop where when it sees the rising edge of the clock, it catches the data. With a latch, well, I mean, you could consider this somewhat similar to an SR latch, because what we do is we just put the correct set and reset values on it to write the data to it. But the read process is slightly different because of the fact that it's in this very tightly arranged grid of memory. We can't just take the direct output. We have to have these extra pass transistors to enable or disable it. So imagine, in fact, yeah, the better way to describe it, imagine an SR latch which So where you're overpowering the feedback loop between the two, between the S and R stages, and imagine them tightly packed in a grid, so you use pass transistors to access it. That's effectively what we've got. Right? Yeah. But yeah, it's definitely not a flip-flop at the very least, because there's no clock signal here as such. Right, and then I suppose the other thing is when we write, we just put the values we want onto the bit lines. We provide them, and we provide them like constantly rather than just pre-charging them, and then we're able to overwrite one of the signals in the circuit. So it'll be whichever one's a 1 will transition to a 0, and then that will allow us to overwrite the other one with a 1. Okay? So that comes back to the question of the memory hierarchy, right? So in maybe the register file, but like definitely the individual stages within the data path, maybe the reg file, right? We would use flip-flops, right? Because flip-flops are the fastest storage element that we've got, because we don't have to go through this complicated read-write procedure. Okay? So that's, and we don't have to have the sense amplifiers, we don't, and also we can access all the flip-flops at one time, as opposed to only being able to address one word of it. So there's multiple reasons why flip-flops are used for inside the data path and in the reg file, and also inside some of the control logic. However, and here's the big however, if we go back to our lecture 17 timing, I think is the correct one, and we have a look at our, no, this isn't the right one. No, I wanted 15, 16, didn't I? Open, folders, lectures. 15 and 16 sequential logic. So if we go back to our sequential logic lectures and look at our fully expanded, well, it's expanded as enough, right? Let's count up the transistors here. 2 for this transmission gate, 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 so that's 8. 2 for this inverter, 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 that's 12 of them. 20 transistors in total to create this flip-flop, okay? Comparatively, if we go back to our memories lecture and we look at our cell, in fact, we've got it written just up here. How many transistors has this got? 6, right? Because we've got significantly less transistors, we can pack significantly more of these memory cells into a given space, and they consume less power, right? So while the flip-flops are suitable for registers or the register file or like little pipeline registers, if we try to pack a large number of them into a small space, we're going to find out that we don't have enough of them, right? And so when we're trying to do like our level 1 caches and our level 2 caches, we use 6 transistor or similar SRAM cells because they're smaller, so we can just get more of them into a certain space. Does that answer the question? Right. I will presume it has for now because we need to get started on the lecture. Right, okay. So last lecture, we saw up to the end of the 6 transistor SRAM cell. We saw how we read and we write to the cell. And we saw the voltage, the pull-up ratio, and the cell ratio that are needed in order to make it work, in terms of making sure that the pass transistors can't overpower the feedback loop when we are reading from the cell, but they can overpower the feedback loop when we are writing to the cell. Okay, so we had to make sure that that was the case. And so we saw what cell ratios we needed for that. And now we're going to move on to DRAM memory, right? DRAM memory works slightly differently, but mostly the same, right? So here we've got a very simple example where we've got so M is 2, we've got 2-bit words. This is just a quick example because it means less lines on the diagram. And we've got 2 row address bits. Oops. And 1 column address bit here. So we've only got 8 cells in this circuit. 8 words in this circuit, each of 2 bits, meaning 16 bits in this memory. This is a very scaled down memory, but it'll be suitable for suitable to just show you what's happening here. Right, so we've got our DRAM memory. Notice we only have a bit line, we don't have an inverted bit line. This is due to the way the DRAM cell works. We don't need the inverted bit line because we don't need to overpower any regenerative stages because it is dynamic RAM, right? We're storing our charge on a capacitor. So we'll look at the 3-transistor DRAM cell first, and then we'll look at the 1-transistor version that we use most of the time, right? So this is the 3-transistor cell. We see that we've got a capacitor here, CS, capacitor for storage, right? And the value of our cell, X, is stored on this capacitor, right? We have a pass transistor over here, M1, which is enabled by the write word line. So this is the word line used for writing. If our write word line is high, this pass transistor turns on, and whatever is on bit line 1 is forwarded through M1 to X, and so we can overwrite the value in our cell. Then, if we look at X and think about whether it's a 1 or a 0, right? We've got a read word line. When that turns on, the bit line 2, which will be initially pre-charged, will either stay as it is, or when the write word line is on, it will be discharged through M3, through M2, presuming X is 0, down to ground. Oh yeah, sorry, yeah, my mistake. Not that one. 5% of you. There you go. Right. Sorry about that. Yes, that might be a bit easier now. And where did my pen go? There. Right. Yes, I've got it. Right. So when we enable our write word line, we can either charge or discharge X through bit line 1. So bit line 1 will be set to the new value, X dash, and we will put that X, we will charge or discharge X to X dashed through M1, which is enabled by the write word line. We pre-charge bit line 2, right? And then we enable, when we want to read, we pre-charge bit line 2, and then we enable bit M3, and then charge on bit line 2 will flow through here. If X is 0, M2 is off, and so it stays at a 1. We see a very slight voltage drop, but it's minimal. If X is 1, then it flows all the way down to ground, discharging bit line 2. We see a significant drop, and hence we're able to read from the cell, right? And then we introduce some sense amplifiers to ensure that voltage drop, because we won't go all the way down to 0, just far enough down for us to notice it. It'll drop down a bit, we'll notice it, and then we'll amplify that up to a real 0, right? Notice, because we're storing our charge on a capacitor, and this capacitor will leak charge, we have to periodically refresh this cell, right? So this cell would have been originally used in one of the very first Intel processors. I think it was the Intel... I think it was the 8080. Give me a sec to just check that. I think I've got it somewhere in here. Oh, right, no, sorry, my mistake. This was the very first Intel 1 kilobit memory chip. So this was a dedicated chip from Intel with 1 kilobit memory, and this would have had an 8-bit word, and then that would have mean it would have had 128 words in the cell. Okay, so that's where this was first used, and it was somewhat popular for a while, because of the simplicity of using it, because you just have to refresh it every now and again. You don't have to worry about destructive reads, which is what we will see will happen with the 1 transistor DRAM cell. So with the 1 transistor DRAM cell, same idea as the 3 transistor cell, in that the data is stored on the capacitance at node X, right? However, this time we just have 1 word line. We're going to use the same bit line to read and write to our read from and write to our cell, right? So what we're going to see is we're going to have something called a destructive read. So first thing we do is we say, right, what happens if we want to write? So we either set bit line to X, or to 1 or 0, that's going to be our X dashed. We're going to set it to that value, and then we're either going to charge or discharge CS through the pass transistor M1 as normal, right? So exactly the same write procedure as the 3 transistor SRAM cell, it's just that M2 and M3 have been cut off here. If we want to read, what we do is we pre-charge bit line to 1, right? And then what we do, oh, is that right? What have we done here? No, okay. So this, it doesn't really matter what you set bit line to, but in the diagram we've got bit line is VDD by 2 by the looks of it, yeah. So we set bit line to VDD by 2, right? And then we enable M1, bearing in mind this is just a stored charge. We're not constantly providing current, we've just stored VDD by 2 on bit line. We enable M1, and then we see whether this goes up or down, right? If it starts to charge up towards VDD, then we know that CS was at a higher voltage than bit line, meaning that X was 1. Therefore, we could, since we know that X was 1, we can then say, right, we know X was 1, we've read a 1, but when we read that 1, we discharged some of CS, because some of the charge stored in CS was redistributed over to CBL, right, our bitline capacitance. So what we need to do is we then run VDD on our bit line, and that recharges CS for us. Can you explain what exactly a read? What exactly is a read? It's done by a scope to read the voltage of the capacitor. You're talking about the one transistor, right? So what happens is we set BL to our VDD, and then we've got some circuitry downstream of BL, right, which senses what happens to the bit line, and then it uses that to drive some logic further downstream. So what you would have is you'd have all these cells tightly packed in an array, and then you'd have some processor which is reading out of that array of data because it needs some particular part of it. So what we do is we store it like this. We have this complicated read procedure, but it then gets sensed by some sense amplifiers, and then it goes into your logic because that restores it to a full swing 1 or 0. Why isn't the CBL capacitor considered in 3 transistor DRAM? Right, put simply because we don't actually use it. So our bit line 1 is only for writing to our cell, right? So it doesn't matter what the capacitance is because we give a constant current to bit line 1 and we want to overwrite X, okay? So it doesn't actually matter because we're storing a lot of charge into CS in that operation. When we're reading from the cell, it would be this capacitance instead, but notice how M2 disconnects bit line 2 from X. When we read from the cell, the capacitor on bit line 2 doesn't really matter because it's not able to redistribute charge from or to X, okay? Because it's separated from bit line 2 by M2. So with a 3 transistor DRAM cell, the reads are not destructive. The bit line cannot redistribute charge to X. Obviously, a write will always be destructive. That's exactly what we want, so we don't care what the capacitance is here because we want to destroy the value on X. The only reason we consider CBL is if we're reading from the cell and we've got a direct connection between our X node and our CBL so that charge can be redistributed. Okay, so charges are blocked by M1 and M3 does not affect the output in... So with M1, it's purely a matter of you want to change X, so it doesn't matter if there's a capacitance on bit line 1, right? With M1, but yes, you're correct. M3 does not affect the... it doesn't affect X in the 3 transistor. Correct, Farron. So yes, back to here. So we said if we start off at VDD by 2, if we see that it starts to rise, then we know that we were storing a 1 at X, and so we then put a VDD onto our bit line and force the charge back into CS. If we see that the voltage at BL starts to drop, then we know that we were storing a 0. Let's make that a bit different. We were storing a 0 in X, and so we force a ground onto the bit line to fully discharge CS, which has had charge redistributed to it from CBL. Right? And then we can say that the delta V, so the difference in voltage, is going to be the voltage at the bit line minus the voltage, what was pre again? I can't remember. minus the pre-charge voltage, which is the voltage of a bit minus pre. Basically, the important bit is this: that we are redistributing charge from CS to CS plus BL. So obviously CS is going to drop. CBL is going to rise in the case that there's a 1 stored on CS. And therefore we then need to force that back high, and we keep that one high because that's the one that we're reading. Okay? So with a 1 transistor DRAM cell, when we read, we destroy the data on our storage node X, and so we need to rewrite that data every time we read it. Okay? That's the main difference between the 1 transistor and the 3 transistor. Obviously, this isn't a great thing, having our destructive reads, but because there's significantly less components here, we've only got 1 transistor here, plus obviously the storage capacitance, as opposed to the 3 transistors here, plus the storage capacitance. That means that this cell is significantly smaller, and it's more useful for creating large memories. So this is what standard DDR RAM is made out of. You've got lots and lots of these cells, very, very small transistors, as small as they can make them, with a parasitic, with an intrinsic capacitance, X at each cell. And then that stores the data, and then they read it through this pass transistor. Right? That's how DDR works entirely. So quick summary of read-write memories. We've got static cells, SRAM, so these are regenerative. Right? The data is stored as long as you've got a supply of power. They're relatively large cells. They're not as big as flip-flops, but they are relatively large cells. So you get fewer bits per unit area. Right, so a chip could be considered your unit area, but whatever your unit of area is, you get fewer bits per that unit area. They're very, very fast. It's not quite so hard to read from them or to write to them. They're much faster, so we use them where speed is important, so that'll be your L1 and your L2 cache. You've got differential outputs, your BL and your inverted BL, meaning that they're more useful if you need the inverted value immediately afterwards. We only use the sense amplifiers for performance. We don't need the sense amplifiers. They can discharge or charge the output all the way. But we say, okay, if we do that, it's going to take a long time for this very small charge to charge or discharge this very large capacitance. So we'll use the sense amplifier to speed it up. And it's compatible with CMOS technology. It can be put on the same chip as your processor logic, right? Conversely, we've got dynamic RAM. So this is a stored charge. We have to periodically refresh the cell. So for DDR specs, so DDR-X for whichever one, 64 millisecond refresh period. They're very small cells, 1 to 3 transistors per cell. Normally it's going to be 1. Most people don't choose 3 transistor DRAM at the moment, because when you get very, very large DRAMs, it's more efficient to just add the regeneration circuitry to rewrite the data back to the cell than it is to use the 3 transistor DRAM. So we get more bits per unit area. It's slower, so it's used mainly for your system memory, for large memories that have to store a lot of data. With the one transistor cell, we only get a single-ended output. So we only get BL, we don't get the BL not that we get with SRAM. So we would then have to add an inverter if we needed the inverted version. And with the one transistor cell, we must have sense amplifiers for it to work, because that very, very small capacitance isn't sufficient to fully discharge the bit line. Okay, so we need the sense amplifiers to have correct operation. And typically it's not compatible with CMOS technology. It needs to be on a different chip. Okay, obviously there are technologies called such as EDRAM. They're very, very rare, but occasionally you'll have DRAM transistors on the same process, but normally not. Okay, so that is the end of the memories lecture. I'm going to then move straight on to the dynamic sequential lecture. This is a relatively short one. Let's see if we can get through it quickly. Question now, how does the power dissipation compare between SRAM and DRAM when they are powered on in the active state and when they are in the idle state? Right, so honestly it depends on whether they're switching or not. So when you are reading or writing, the DRAM generally has a lower power, okay? Because if we just quickly have a look back at this, so when you're reading or writing this cell, you have to overpower this very large feedback loop, right? Especially when writing to one of these cells takes a lot of power, because you've got a short circuit power when you're overwriting the feedback loop, right? So this one consumes a lot of power when you're doing the read or write operations. Conversely, if we look at the one transistor cell, with this cell, the amount of power consumed to read or write, well, you consume a little bit of power either charging or discharging CBL, and then fully recharging or discharging X. But other than that, you're not really consuming much power in the dynamic transition, because you're only discharging this tiny little CS capacitor or the relatively small CBL, right? So dynamic switching, when you're reading or writing, the one transistor cell is less power, and probably the same with the three transistor cell as well, that will be less power. However, when idle, this cell consumes very little power at all. There's only the slight amount of leakage through the transistors, and because they're high VT transistors, they're designed to have low leakage. That leakage isn't particularly high, right? So you end up with a cell that doesn't really consume much power when it's idle. Although obviously there are more transistors, but yeah, in general it doesn't consume much power. Conversely, the one transistor DRAM cell and the three transistor DRAM cell, because we have to refresh the logic periodically, and we have to recharge that X node again and again and again, and each time we read from X and then we recharge it, doing that consumes a fair bit of power. So static DRAM consumes more power. So you could normally see this if you have a suitable power monitor on your computer. If you have the tooling to do it, what you would see is that when your processor is completely idle, it'll drop down to a fraction of a watt, while your memory will be consuming more like 4 watts, right? For example, on a desktop computer. Whereas when you've got your system active, you'll see that your processor, both in terms of logic and in terms of its memory, is consuming multiple watts, whereas the DRAM power doesn't really change much. right? So we say that the static cell consumes more power when it's switching, when it's reading and writing, whereas the DRAM cell consumes more power idle. Okay? But that is completely dependent on the exact technology, mind you, so that's just a general look at these things. So, sequential dynamic, right? So this is a relatively short lecture. I hope we'll be able to get through it today, but if not, we'll just finish it off on Monday, or we might just finish it off today and run slightly over. Right, so dynamic sequential. When we did our dynamic circuits, we saw how that the dynamic circuit stored the value on their intrinsic capacitance for the remainder of the clock cycle. So we put a value through and then it sort of held that data there until the next pre-charge cycle, right? However, what happens if we want to store data for longer than a pre-charge cycle, if we want to store data from one pre-charge cycle to the next, right? Well, we need to start introducing some bigger sequential elements. So let's try designing a flip-flop in dynamic logic, right? Now, the benefit of dynamic logic is that we have capacitors we can store values on. We don't need that regenerative bistable feedback loop that we have with our static logic, right? So rather than that, we can just have a capacitor, right? So what do? We have two capacitors, two stored values, just like we have in our static logic, two regenerative feedback loops. We have a transmission gate to enable or disable charging or discharging of these capacitors. We only need one transmission gate this time because it's okay to have this as a high impedance node. Because it's dynamic logic, we can leave a node either charged or discharged. So we have our two transmission gates to enable or disable each side, and then we have an inverter to act as a regenerative like level restorer, actually would be a better way to put it, level restorer, right? So we have a master slave situation as before. So we have a master unit which, while the clock is low, so clock equals 0 and not clock equals 1, this transmission gate T1 will be turned on, and so we'll charge or discharge C1 appropriately, and the value will propagate through to QM, our midpoint in our circuit, right? The slave, on the other hand, is transparent, so clock equals 0, not clock equals 1. We see that this one is currently turned off. Okay? And so I2 is driven purely by whatever was stored on C2. Then we switch our clock round. We have not clock goes to 0, clock goes to 1, clock goes to 1, not clock goes to 0. Therefore, T2 turns on and T1 turns off, meaning our master is now holding the value. So whatever was on C1 before the clock edge stays there. It's pushed through I1 and inverted, through T2 because T2 is now transparent, into C2. So C2 now gets charged to whatever was on QM. And then also through I2 to Q, right? So if we had a 1 on D before the clock edge, and our Q, so let's say we have a 1, D, clock, Q, Q on the clock edge will transition to 1. It was originally 0 because QM if we look down from Q, from D, QM would have transitioned to a 1 at this point, and then at this point QM gets propagated through to Q. Okay? So exactly the same style in terms of using a master flip-flop and a master latch and a slave latch to create a flip-flop. But the difference here is that rather than having the feedback loop and having to cut off that feedback loop, instead we can just store the value on these capacitors. Right? The setup time is purely the time taken for the signal to propagate through T1 and be stored on C1. The hold time is 0 because the moment the clock switches, T1 turns off before C1 can discharge, or charge, whichever way round, before it can disturb C1. So we've got a hold time of 0 because T1 switches off instantly from the 50% point of the clock. TCQ, the time from the clock edge to the output becoming valid, well, we have to go through I1, I2, and T2. So we've got 2 inverters plus a transmission gate in terms of delay. Obviously C2 is included as part of the delay of a transmission gate, okay? And similarly C1 is included as part of the delay of this transmission gate, right? C1, C2, the time taken to charge up those capacitors, because they are the gate capacitance of I1 and the source or drain capacitance of T1, for example. Okay? So, just like our static flip-flop, just a different storage element. Obviously, just as with the static storage element, we need to consider, well, what happens if our clock and our not clock aren't exactly aligned. So we can have 0, 0 overlaps and 1, 1 overlaps. Well, let's have a look at them. In the case of a 0, 0, clock and not clock are both 0, meaning this transistor's on, that one's off. This one's on, that one's off. So therefore, a value can propagate through to C1, through I1, through to QM, then through this transistor to C2, and result in a disturb on Q. So on the negative edge of clock, presuming clock runs slightly before the inverted clock, we can see that whatever's on D can go all the way through T1, through T2, out to Q, and cause a transition, right? So we have to define a constraint. The overlap time, so the width of this blue bar, T overlap 0, 0, right? The width of this blue bar must be less than the propagation delay of T1, I1, and T2 to make sure that it cannot disturb C2 when the clock goes low. We also have a 1, 1 condition, right? This transistor and this transistor can be on at this point, and so we have to guarantee that we hold our data. So from the positive clock edge here, we have to hold our data for longer than the overlap period, because if we don't hold our data for longer than the overlap period, our C1 can become charged up, and then because our clock is high, this T2 over here is currently transparent, so it can propagate that value on C1, the disturbed value on C1, at any point in time, because this one is currently transparent. So we only need to disturb C1 for it to become effective. Okay, so we've got a hold time constraint and an overlap constraint. Well, we've got two overlap constraints, one of them relative to the hold time and one of them relative to the delay of these inverters and transmission gates. Obviously, we can set our hold time, we can define how long our data has to be held for, so this is relatively easy to meet. This one is harder to meet if we find that this is... we've lost our pen. If we find that the overlap is actually longer than this, so we just need to increase the length of these gates or increase the width of this capacitor or the length to increase the delay and therefore make it bigger than the overlap time. Or we can just decrease the overlap time by generating our clocks better. So yeah, these constraints are a bit awkward for us. Is there something better we can do? So this is a scheme called clocked CMOS, C2 MOS. Again, it's a flip-flop. We've got a master latch and a slave latch put together to make a flip-flop overall. But this is slightly different, right? This one we will see is clock skew insensitive. It doesn't matter if there's a difference between clock and not clock, right? So 8 transistors as before. So if you look at this circuit, we've got 2 transistors here, 2 transistors here, 2 transistors here, 2 transistors here. We've got an 8 transistor flip-flop compared to, and I'll just put dynamic, compared to the static, which is a 20 transistor flip-flop, right? So we've massively reduced the number of transistors in this. Again, we're at 8 transistors. It's still dynamic logic, but it's a slightly different scheme, right? So when the clock is low, these 2 transistors are on, because clock is 0, not clock is 1, so these 2 transistors are on, and so the data on D will be inverted by this inverter. We'll go straight through these and run on QM, right, and be stored in C1. On the other hand, our slave, because this is 1 and this is 0, these 2 will be off, and so C2 will just hold its value. When our clock goes high, these 2 transistors turn off. Therefore, C1 now holds its value. Changes on D cannot propagate through to C1 and QM. However, these 2 transistors turn on, and so the value on QM is inverted by the M6, M5 pair and their gates, and then driven through M8 and M7 to Q. So the slave is transparent and the master is hold in its hold state when the clock is high, other way around when the clock is low, and on the clock edge, data that was on QM gets propagated through to Q. So again, it's a flip-flop. So let's have a quick look at our 0-0 overlap case. So we saw in the previous circuit that in a 0-0 overlap case, because we had a transmission gate, well, 2 transmission gates, we could see that the signal could propagate through the 2 of them to the output, right? It wouldn't be a perfect propagation because in one case you'd have a 1 going through an NMOS or a 0 going through a PMOS, which wasn't great, but it could still disturb the output. However, with this circuit, we'll see that it's actually not going to happen that way, because we see that our PMOSs are only driving 1s and our NMOSs are only driving 0s. So we can't have the case of an NMOS driving a 1 as a pass transistor or a PMOS driving 0 as a pass transistor. So we'll assume that we make a change on D and it propagates. So obviously D must be 0 for this to even start propagating. It gets to M2 and it tries to upset QM on this 0, 0 overlap. It gets down to here and we see, oh, clock is 0, therefore this transistor is off. So we can upset QM if we have D is 0 and we've got a 0, 0 overlap. So this QM, rather than being a 0, it gets disturbed to 1, but we end up with it being stopped at our M7, right? Because we're not using pass transistors here, where we can only drive a 0 with the NMOS, and we've actually got a 1 here, right? So that's not going to happen, right? If we look at the 1-1 overlap case, in this case, if we imagine D is 1, okay, it can disturb QM. We can get a 0 here, where it should have been a 1. And then that 0 can turn on M6, but M8 just here is off, meaning it can't disturb Q, right? Only unfortunate thing is that this is happening during the hold time, where M8 is off. When our clock goes low again, M8 will turn back on, right? So if we manage to disturb QM, then we'll see that when our clock goes low, that disturbed value of QM will then be able to propagate through to Q. So we have a 1-1 overlap constraint where the hold time must be longer than the overlap to make sure that we don't have that we don't get our value propagate through on the falling edge. Okay, so we have that small 1-1 overlap constraint, but other than that, it is completely and utterly insensitive to clock skew. And so with this, we've created a dynamic logic version of our flip-flop. Obviously, we have the constraint that, given that we're storing charges on these capacitors, we have a refresh period that we need to observe. We must change our data at least every now and again. Like, we can't leave our clock low for more than so many milliseconds. So we cannot have our clock low for more than our refresh period, but other than that, we've got our dynamic flip-flop in 8 transistors. Okay, and so that's how we would do this in a dynamic style. And so in a very high performance processor, we would probably use this type of dynamic flip-flop rather than a static flip-flop, so that like during our data path, so that we can make use of it, make use of the smaller transistor and the faster switching time. Okay, and that is the end of the sequential dynamic lecture. So that one was a relatively quick one. Is there any questions? No? Okay. Well, that is effectively the last lecture, if I remember rightly. Let's just have a quick check of that thing. Open folders, lectures. So there was going to be a revision lecture, so this was mainly designed for the fact that there was an exam on this unit. Obviously there's not going to be an exam on this unit, so this was a quick revision lecture with exercises going over the most important points that you needed to know for the exam. So mainly over logic design and timing, and looking at the critical paths. Yeah, most of the revision lecture was timing because that's the one that people find most difficult. But yeah, we won't be doing that one this time because obviously there isn't an exam. But if you want to, it's worth having a quick look through it. Have a go at this exercise so that you know what it looks like. So that you can know that you can do it correctly, and have a go at some of these critical path things where you just have to work out what the paths are through this circuit. Check your answers. It'll be just like a good exercise on timing, okay? And possibly even there isn't a pipelining one here, is there? No, shame. But yeah, so just have a quick go at this to make sure you remember how it works. But other than that, that is the last lecture for VLSI design. I hope you learnt something. Can't really test it because obviously there is no exam. So, and then some of you will be 4th years and going out to industry now. So good luck, especially if you're doing a career in VLSI design. I hope this has been helpful. Yeah, I'll give a quick pause for questions and then that will be it from me. No? Okay. So yeah, good luck. I hope you all do well in the rest of your assessments. Almost finished marking lab 3, so that should be up sometime within the next few days. And yes, by all means, email me if you have any queries or doubts, or anything that you just want to find out about. Yeah, that'll be it from me. See you.